We are going to look at some application problems in this section. So it's called the rates of change in natural and social sciences. The idea is there obviously are a lot of applications to derivatives. If you look on here, I have some listed below. So applications in physics, which you're going to do the most often. We're going to look at velocity acceleration given the position function. We've already done this. We're going to do more with it basically in this section. Chemistry, we can look at the rate of a reaction. Okay, so I have a reaction happening and the reaction's rate of change. In biology, rate of growth. We'll do more with that later. This section is really going to talk about the physics and the economics, the marginal cost function. Are the two that we're really going to look at. So the marginal cost is really new. So instantaneous rate of change of cost, if I have some function, a cost function, A is my overhead. The other terms have to do with raw materials, labor. The cost of raw materials may be proportional to X, but labor costs might depend partly on higher power. So this is just saying how much it costs to make 10 products, how much it costs to make 100 products, so on and so forth. And then we'll look at what does the derivative of that stand for. Okay, so just to quickly review, in a particle problem, if I look at a particle problem, okay, how do I find first quickly velocity? So in a particle problem, if I want to find velocity, okay, so if I'm given position function, in these problems, you are usually given the position function, which is usually s of time, s of t. I want to find velocity. That's just the first derivative. So that would be the derivative of the position. Acceleration, sorry, this is first derivative. Okay, acceleration would be the second derivative of position, or the first derivative of velocity. If you're given position, to find velocity, you find the derivative. To find acceleration, you find the derivative of that. Okay? To see where I'm at rest, or when I change direction, that would just be where velocity equals 0. Obviously, my velocity is like your speed, but it has direction. So if velocity is 0, then I'm not moving at all. When am I moving to the forward or the right would be when velocity is greater than 0. And left would be when velocity is less than 0. Should make sense. Okay. Total distance traveled. You're going to have to figure out how far did I go moving forward, how far did I go moving backward, and add them together. Okay. And then speeding up and slowing down a little bit harder. So speeding up, both velocity and acceleration have the same sign. They're either both positive or both negative. That's when I would actually be speeding up. Both positive just means I'm going to the right in speeding up. Both negative just means I'm going to the left in speeding up. Okay, slowing down is when velocity and acceleration have opposite signs. So this is just kind of the key to how to do it. And now we're going to do a problem to actually get these values. Okay, so here you go. Here's the position. Like I said, most of the time you'll be given position. So find velocity. Velocity would just be the derivative of that. So position's your s. So my velocity would just be, take the derivative of that quickly. I have 3t squared minus 12t plus 9. There's my velocity function. What's the velocity after 2 seconds? I would just take that, plug 2 in. So plug 2 into that answer, and I get -3 meters per second. After 4 seconds, I could take my above equation, plug 4 in, and you should get 9 meters per second. So pretty simple. We've done this. You found velocity before, velocity after a certain time period, given position. Okay, that's pretty simple. Now, when am I at rest? So now I'm at rest when my velocity is 0. So now I would take my velocity, set it equal to 0, and solve. Okay, so at rest, meaning it's not moving, meaning my velocity is 0. Divide by 3. I could leave a lot of this algebra up to you guys. Factor. Most of them factor, honestly. If they don't, I'd have to use quadratic formula. So I would be at 3 and 1. So after 3 seconds and after 1 second, I'm at rest. Okay. Now, when am I moving forward? I'm moving forward when my velocity is positive. Okay, so now the easiest way to keep track of this is make a quick number line. So here's my number line, my velocity number line. My velocity is 0 at 1 and 3 seconds. Now I'm going to figure out, is my velocity over here positive or negative? So when the time is 0, plug 0 into my velocity equation here, and I would get what? 9. So it's positive, which means I'm moving forward from 0 to 1 second. Now I'm going to plug 2 into my velocity equation. You could either plug it in factored or original. It doesn't matter. Okay. If I plug 2 in, I get a negative times a positive, which is a negative. And then if I plug 4 in, I'm going to get a positive, which means I'm moving forward from 0 to 1 second. Then I'm moving backwards from 1 to 3. Then I'm moving forward again, 3 to however long I go. If it doesn't tell me, I'm going to write infinity. So forward would be 0 to 1, 3 to infinity. Backward would be 1 to 3. Okay. Pretty simple. Forward, backward. Draw a diagram. So this is just to kind of see what's going on, what I kind of just said. So it's not a graph. It's just literally particle starts here at time equals 0. It hasn't gone anywhere. Okay, from 0 to 1 second, I'm going forward. So I can put this little arrow. Time equals 1. And then from 1 to 3 seconds, I'm going backward. Now I don't know how far I'm going yet. So this is time is 3. And then I'm going forward again. This just shows a quick visual that the particle goes forward for 1 second, backward for 2 seconds, and then forward again. I have not calculated distance yet. I'm going to show you how to do that next. Okay. So now for total distance, I need to split it up. I can't just do beginning and end. So for the first 5 seconds, I would have to go from 0 to 1, and then from 1 to 3, and then from 3 to 5. Okay, why 1 and 3? Because that's where it changes direction. I've already figured that out. So first you got to figure out where does the particle change direction, and then you're going to split it up. So you have to know how far did I go from here to here, and then how far did I go from here to here, and then how far did I go from here to time equals 5. And then I'm going to add these 3 numbers up. This one's actually going to come out negative, but I'm going to take the absolute value. Okay, so now how do you actually figure that out? So I would just, simple, if I want to know how far I went from time 0 to 1, I would plug them into my position original function and figure out what was my position at 1 second. And then I put t here. And then what was my position? So s of 1 minus s of 0. That's going to give me how far I went. So when you plug 1 into the original equation, my position function, and I plug 0 into the original, I subtract the 2, that's going to tell me how far I went. It's going to tell me my original position and then how far I am here. Okay, so again, the only thing you have to remember is I'm plugging it into original, not velocity. Velocity, I'd get 0. So I go back to this, I plug 1 in, I plug 0 in, I subtract the 2, and I get 4. And then I do it again. So this one would be s of 3 minus s of 1. Again, I get 4. And really, I need to take the absolute value of these. Because if it comes out negative, all that means is I went backwards. I still want the positive value. I want to know how far I went. And then I would do s of 5 minus s of 3. And this is 20. And then to get my total answer, I add all these together and I get 28 meters. Okay? If you just did s of 5 minus s of 0, that would not give you total distance. It would give you displacement. It would tell you where you started and where you ended and how far apart you were. But it wouldn't tell you how far you went in between. Okay? And then a couple more questions. Find the acceleration after 4 seconds. So acceleration is the derivative of velocity. So I know that my velocity equation we had was 3t squared minus 12t plus 9. So acceleration would be the derivative of that, which is 6t minus 12. And then after 4 seconds, just plug 4 into that. So a of 4 would be 12, and I'm going to be in meters per second squared now for acceleration. Okay. And then the last one, when am I speeding? This is probably the hardest one. Okay, so I'm speeding up, remember, when velocity acceleration have the same sign. So again, I'm going to go back to my number line. We've already done a number line for velocity. Okay, my velocity number line, I was at 0 for 1 and 3. And I was positive, negative, positive. We've already did that. Now I'm going to do the same thing for acceleration. I'm going to figure out when is acceleration positive and negative. Okay, so my acceleration is 0. Look at this. When would this be 0? When t is 2. So 2, acceleration 0. And numbers to the left of that are going to make acceleration negative. Numbers to the right of that are going to make acceleration positive. Okay, so now I have to compare these two. When are they both the same sign? So if I look, they're both negative from 1 to 2. So here would be 1, right? So from 1 to 2, they're both negative. And then if I look from 3 to infinity, they're both positive. So this is when I would be speeding up, from 1 to 2 or 3 to infinity, because both velocity and acceleration are the same sign. And then they're opposite signs if I look from 0 to 1 or 2 to 3. This would be slowing down because they have opposite signs. Okay. And then lastly is a marginal cost problem. So company has estimated the cost in dollars. So this is just a cost function. If I plug 1 into this, this is going to tell me what does it cost the company to make one, say, candle. If I plug 10 in, it's going to say how much does it cost the company to make 10 of them. Your marginal cost function is just the derivative of the cost function. So this is just your derivative, which means the rate of change of cost. Is it increasing or decreasing? Okay, at some point it's probably so it's going to increase for a while, say to make 0 to 100 candles, and then at some point it's actually going to get cheaper to make more of them. So my derivative of the one given is just, if I look, 5 plus 0.02x, there's your marginal cost function. Part B is saying find the marginal cost at the production level of 500. So that's just saying plug 500 in, and then what does it actually mean? So if I plug 500 into the derivative, I get $15. So that's not what it costs me, that's the rate of change. So that's saying the rate of cost is increasing by $15 when 500 things are made. So if I make 500 candles and I make 501 candles, it's going to cost me $15 more to make 501 candles than it does 500. So the rate of change of producing this many things is this amount. Okay, and if it were negative, that just means that it's decreasing. It costs me less. And then I think I have one more question to go along with this. So the last one's find the actual cost of making that item. So now if I want to do the actual cost, if you plug 501 into the original, and if you plug 500 into the original function, and I subtract the two, that would actually tell me the difference. Okay, so if I go back to the original, plug these in, and subtract them, it comes out to be 1501. Whereas the derivative told me 15, so it's really close. That kind of gives you an idea of what it's finding. So to make 501 of them, minus to make 500, it's $15 more to make the 501st thing versus the 500th.